In this data set, I've got 8 people, 4 men and 4 women. The first 3 men are all treated. The last guy, he's not treated. The first woman, she's treated, and the other 3, they're not treated. So we see that treatment doesn't look like it's randomly assigned here. It seems to be correlated with gender. 75% of men are treated, but only 25% of women are treated. So what can we do? Well, under the unconfoundedness assumption, we can assume that among the females, treatment is randomly assigned, and among men, treatment is randomly assigned. Under that assumption, we can compute from our data the conditional average treatment effect for females and for men as follows. So once we've gotten our data, we're only going to see one potential outcome. So for the first female, she was treated. So we see her outcome when she was treated. We do not see what would have happened if she wasn't treated. For the other 3 females, we do not see what happens if they had been treated, because they weren't. Instead, we see what happens when they weren't treated. So we see these 3 potential outcomes. So using this data, we can compute an estimate of the conditional average treatment effect for females as follows. Take the average among females who were treated, 75, subtract off the average outcomes among females who weren't treated, and that gives us an estimate of the conditional average treatment effect of minus 11.67. And we can do the same thing for men. We take the average among men of the outcomes who were treated, get this number here, subtract off the average outcomes for men who weren't treated, and that gives us an estimate of the conditional average treatment effect for men of 20. Now, over here in this column, I've shown the unit level causal effects. With this, we don't see in our data, but with these numbers, if we knew them, we could compute the true conditional average treatment effect. For females, it's just the average of these 4 numbers, and for men, it's just the average of these 4 numbers. Now, those numbers aren't going to exactly equal this number here for men and not this number here for women, because these are just estimates. Okay, but if we had more and more and more people in our data set, if we added more men and more women, then this number would slowly get closer to the average of the numbers in this column for females, and likewise for men. Okay, so now once we've gotten our conditional average treatment effects, we can combine them to get the overall average treatment effect as follows. You just take the conditional average effect for men, multiply it by the proportion of men in the sample, which here is just 50%, so 1/2. Add the conditional average treatment effect for females multiplied by the proportion of females in your sample. Again, here it's just 1/2 because there's 50% females. And that's going to give you an estimate of the average treatment effect. In this case, 4.16. So that's what you're going to do when you get your data and you make the unconfoundedness assumption. Do your analysis just like in a randomized experiment, but within each group, and then combine the groups at the end to get your overall average treatment effect. Now here's what you definitely should not do instead. Instead, just ignore the fact that you have data on men and on women, and then just look at the average outcome among people who were treated, okay, that's this number here, and subtract off the average outcome among people who weren't treated. That's this number here. In this case, you're going to get 78.75 minus 80, or minus 1.25, which would suggest that the average treatment effect is actually negative. The treatment's bad. Whereas over here, we got a positive number, so the treatment's good. But this is not what you should do, okay? Because remember, this is what you do when treatment is randomly assigned. But here it's not. It seems to be correlated with gender. Men are more likely to get treated. So this is not getting you the actual average treatment effect. You should not do this, okay? Do not do this. It's wrong. This is what you should do instead if you're going to do an analysis based on the unconfoundedness assumption.